Good morning. For those of you who are not from Boston, welcome to Boston, and this is my home base. Our company is headquartered in Boston, and hopefully you get some time to kind of explore the city and enjoy the weather. Thanks, Keith, for inviting me. Since I am from industry, allow me a couple of minutes to just introduce the company that I work for and what the heck we do, and why am I here. We are a risk modeling firm. We call ourselves catastrophe risk modelers, meaning our lives are all around thinking of extreme risk. In generally any problem, we are serving primarily the insurance, the reinsurance industry, because they are dealing with risk. And we do serve governments because much of our work can be applicable to all other sectors of the economy. My colleague David Hogan spoke earlier today. We are actually colleagues because we are sister companies owned under the same umbrella company called Verisk Analytics. What do we do at AIR? When I talk about catastrophe risk modeling, much of our time is spent in thinking about risk for natural catastrophes, crop and agriculture, and that's why I'm here, climate change, life and health, mainly diseases, disease modeling. And we call global connections. These are emerging risks. Think about how many times you think we hear about cyber being the next emerging risk. Think about disruptions to global supply chains. And there are elements of it in crop and agriculture as well, because the world is so inherently connected today. So what's happening in China does impact what's happening in the United States. So those are the 5 major areas that we spend our time and thought process in. Now, to drill into crop and agriculture, I'd just like to say that there's another dimension, which is what we do is very global in nature. So we are not only thinking about the set of problems in the United States, but our reach goes globally. What you see here shaded in green are the countries where we have solutions, not necessarily in crop and agriculture, but that's our ambition to have the same level of coverage for crop and agriculture as well. Now, very briefly, why do we exist and how did we come about to solve what class of problems? So the fundamental problem is, think about year 2012, the United States experienced some extreme drought and there was failure of crop. And if you ask the question, for the country as a whole, what's the probability that we would see something like that or worse? Or what's the probability of any other year that we have already experienced in the last 30, 40 years? So that's really the fundamental question, and then the applications of it come about from answering whole set of questions if we can answer that fundamental question. So our approach is not purely data-driven. I know this is a big data conference, so what you'll hear from me is unlike big data in the technical sense, but towards the latter half of my talk, I'll show you examples of where we are headed, and some of the things that Steve just spoke about is where we'll kind of theoretically go towards big data applications. So what we do is, if we look back in history, we see the data, and you are economists, so you know data is always contaminated with many effects. So in the world of crop and agriculture, there's weather, which is probably the primary factor that explains the variability we see in crop yields and crop production. But then there's, over time, technology has changed. Since we are in the world of insurance, that data is further contaminated by how the insurance world has changed in that period of time. So just by looking at the historical data, it is very difficult to say, okay, I'm going to detrend the data, or I'm going to somehow isolate the effects of all these things that have changed in time. Rather, we say, let's start from the ground up. And we recognize that if weather is the fundamental driver of variability we see, then let's see if we can model the weather. And then layer on top of that these other components. So we start with what we say, let's model the hazard. So conceptually, we are saying, if we look at the United States, we know there are so many climates because the United States is as large as a continent, and can we model many realizations of weather as it evolves throughout a growing season? And our basic model is based off a Monte Carlo framework, which essentially for us means, can we simulate weather thousands and thousands of times in the current climate that we live in today? because I just wanted to bring in climate into the discussion because that's important to us. We are not talking about what was the climate in the 1920s, neither are we talking about what's the climate going to be in 2050. So we are talking about in the world we live in today, given the extent of climate change that has already happened, can we simulate thousands of realizations of how the next year's weather is going to look like? So that's really the primary force of developing a hazard. Then we can say, okay, now we take corn, we take soybeans. Do we understand what's important to corns and soybeans as it goes through the growing season, from planting all the way to harvest? So we develop indices to model some of those physical processes. And then we say, okay, now if we know the evolution of weather during a growing season, we can predict or estimate at the end of the season what's the crop yields going to look like. Then we bring in all insurance and financial conditions. In this way, we try to separate out all the effects. So again, one of the novelty of the approach we have developed is introduction of what we call a weather index, an AAI, which is essentially a cumulative index of what happens to a particular crop as the soil temperature, the moisture, the overall humidity varies through the growing season, and can we boil it down to an index which we can use as a predictive variable to kind of say what's going to be the yield at the end of the season. That's kind of one of the areas that we have innovated so that it allows us to isolate some of the effects that I was talking about. Now, if we do that, at the end of the day, we can then say, okay, we have simulated crop yields over thousands of years. And today you see this map I'm showing you as county level maps. So there are 2 points I'd like to make. One is the work we are doing today does require a lot of data. It's not technically big data yet because these are still things we can handle in large enough servers, but we don't need to go to supercomputers yet for the work we are doing here. Secondly, if you see these maps, one thing that stands out is we need to think about correlations, right? Because the weather is not random, because there are patterns we see, but there are certain spatial correlations in the weather we see. And therefore, there are spatial correlations in the crop production that we would expect. But there will be still variability from one farm to another because weather is not the only factor. So what we do and offer today is a set of models. We call these multi-peril crop insurance models. For the United States, we have it for China. We model crop hail, damage to crop for understanding how extreme hail can cause losses, and so on and so forth. The other area is the models we develop are somehow developed unconditionally to what's happening in the current growing season. What I mean by that is most of the modeling is we look back the last 40 years and say, okay, this is the variability in weather we have already seen. Based on that, we are going to extrapolate what is the total range of variability we would expect in the future, so that we can say with certain probability next year or this growing season, now that we are still kind of in the middle of the growing season, what could be the end outcomes. But we can also now conditionally say, well, we are in the end of July. So what has happened already here to date, and conditioned on what we already know the weather has done, or if there is skill, we can estimate what's the next 3 months going to look like. Then we can conditionally say, okay, this season is going to look very different. And then now we are getting into forecasting, if you will. That is still an emerging area for us because, as you very well know, predicting the weather is not easy. Even with the best of science, the skill levels kind of die out after a few weeks of forecast periods. So that's what we do today. Now let's get into where are we headed and why does big data matter to us. So what I've talked about is conceptually the problem at a little macro scale. Now, the problem is the same even if we now go to an individual farm, right? So if we say, what's the probability that this parcel of land is going to produce a bumper crop or completely fail? So now that basically means that we are now telescopically looking at a higher resolution. We want to get into the area of real-time monitoring, and we have already heard about a lot of applications coming out with satellite-based observations or other remote sensing observations. And since the world is globally connected, we need to start asking the questions. It's not good enough to know the correlations of what's happening in California versus Florida or the Midwest, but now we are talking about what's happening in Brazil versus the US versus India versus China. That's another area where we need to understand, and there is a particular reason why that's important, and I'll just allow me for a minute to kind of digress a little bit. So there is something called the world of reinsurance, which is all insurers who have insured farmers, they eventually take all that insurance that they have sold and they transfer it to a company called a reinsurer. So these reinsurers, basically they are financial institutions putting out capital for a certain price. They work globally. So for them, the portfolio of risks that they take on is inherently global in nature. So it is important then for them to understand, okay, if I'm writing or putting out so much capital in China, is it correlated with what is going to happen in the United States? So for us, it's important to understand those correlations. And I'm running out of time because I've been given the 5-minute warning. So one of the things we want to do is make sure our models are physically motivated. So that's a slight departure from just the big data thought process. We are using and consuming volumes of data, but we still want to make the models physically realistic and physically driven. So these are kind of weather patterns that you observe on television every day. But now what's not obvious is, can we generate this weather at that very farm level? And it's not easy because we'll never be able to put in as many sensors for observing weather at the very granular scale. So there will always be a need for taking sensor data at certain sparsity, marrying it with model data to make a coherent understanding of what's happening on the weather. So that's one area that we tend to spend a lot of time. We have already done some of the work to model flood risk for the whole United States and so on and so forth. So there are derivative works that we can use in crop. The other area, coming back to my theme of global correlations, is we are looking at how do we model weather now at the global scale around the globe and still make sense out of it. So it's not that we are not observing weather, we are certainly observing data, but our job is, can we understand those extremes and therefore the combinations of the worst and the good outcomes of weather. What you're seeing here in this exhibit is simulations of wind velocity, if you will. We are looking down the North Pole over Earth, the northern hemisphere, and U and V stand for 2 directions of wind velocity at a certain height at the atmosphere. So on one panel, that's actual observations. Another panel is a purely stochastic simulation from a model that is trained with observations. So I would kind of just ask you, can you differentiate which is the model versus which is the real observations? So in the interest of time, I'll just say that it's actually quite hard unless you have a real trained eye to look at these patterns. But in general, I think it is suffice to say, I think we are getting to a point where some of these patterns can be modeled using stochastic techniques. And if we are able to model the large-scale atmospheric flow on a globally correlated basis, then we can region by region go and employ another layer of very detailed models to come up with the weather patterns. And of course, this is where velocity and the volume comes about big data. In order to build these models, we have to think about so many things: land use, land cover, temperature, precipitation, where are the lakes, where could flooding happen. So just the amount of data in each of these areas is exploding because we are observing these things using different techniques and different sensors. So we are ingesting now terabytes of information to drive the next generation of models. Now, where will this lead to with respect to crop and agriculture? Of course, there are some very obvious applications. We are already monitoring crop health. There are so many other private companies who are doing it. This is being done in academia using satellite observations. Now the question is, how do we translate them into valuable products that can be operationalized? So that's one area that we envision that there'll be a lot of rapid development. I've already talked about weather modeling at a large scale. I'm seeing companies who have come up with different types of weather observations. All cell phones, they are deploying techniques to collect weather data globally. And so now if that is kind of either through social media or cell phone networks, we can collect that data, then maybe now that introduces a new variety and a new set of data sets that we can use. Everything I've talked about, I have not used the word machine learning yet. So we heard about support vector machines, but that's the world we are entering, because once the data gets to a volume, good old techniques actually will not work. But I think it is still important to understand that sometimes we just cannot blindly go with the correlations. The causality cannot be forgotten. So our approach is still have domain experts look at it. So if we run support vector machines on globally observed weather for the last 40 years, it comes out with these wonderful correlations. But sometimes we scratch our heads and say, does that make sense? So we would like to ask our climate scientists, does that make sense, before we just blindly say, yeah, we saw a correlation and let's run with it. So that's one last word I'll say. Very brief, just give me a second. So where are we with crop and agriculture? Just in case you are interested, of course, we do US and China. We are actively working on Canada right now. And the purple countries are where we are going next, India being the very next one. We are working with academia. We like to collaborate with, in the United States, with various agencies. So we cannot do it all alone. We are a group of about 100 scientists and engineers right here, actually a block away from here, where we do all the work that I talked about. And thanks for your attention. Thank you.